Okay, hello everyone and welcome to Handmade Hero, show where we code a complete game live on stream. We are going to take a look at doing some lighting refinement today. It's actually kind of getting to a nice spot, honestly. I have been liking the lighting more and more as we go, especially because in general these are not the sorts of systems that anyone really knows how to do well. So it's always kind of a little bit of an exploration to figure out how to put something in there that's nice. In general, though, we still are not quite there yet. Like, what? Well, I feel like we kind of have to click on that button. How likely is I would recommend? That's hard to say. I mean, I guess I wouldn't know what else to recommend, so in that sense, I'm extremely likely. If you're asking how much I like it, well, it's like a 0 or a 2 or something. We'll say 5, because I don't know. What changes would this get high rating? Much better performance. Let's see, what else do we want here? I think that's the biggest one. What other sorts of things? Don't pop up license windows and survey windows in the middle of me trying to code. Get rid of all the weird crap like the yellow flag that shows up in the corner and the web startup stuff, and stop installing an SQL server and 15 million services just to run the debugger. And probably the other thing would be don't require an install at all. Just make an executable that runs like a normal program. Yeah, I think that's basically it. For debugging stuff, make a way to view images in the debugger, like a pointer to an RGBA, and you can specify the width, height. Make a way to view 3D data, like you can point to a float buffer and view 3 floats at a time in a 3D window. What else would I like? Make it instantaneous to step in the debugger. Right now it's very slow. Update the watch window instantaneously. Right now it lags way behind the step. See what else we got here. Make sure the compiler is just one exe that can be installed by itself with no dependencies and just called directly with no VC vars or anything like this, or DLL path or nonsense like that. Output AST to a file via command line switch, so I can, in a well-documented format that I can easily load with no DLL or libraries, just a simple single flat file load, and then parse it myself easily. Clean up the PDB format so that it's simple to read and parse and use. Etc., etc. The debugger reads PDBs reliably and shows the source code and disassembly reliably, which is nice. Everything else about Visual Studio's pretty bad these days. What source control tools, home, or sorry, proprietary in-house? What challenge do you cover when using these tools? None? Sure. Congratulations, guys. We filled out the survey. What do you think? All right. So moving on. If they want to follow up, they can just watch the show. They see me use the debugger all the time. Watch me stepping through and the watch window still shows results from like 10 years ago. Apparently there's like a watch update lag parameter that you can actually change that will speed that up. Because I guess it's just so slow that then it makes stepping slow. So what they did is they decoupled the two, which is crazy. It's so nuts. You're like, wait, instead of fixing the problem, you made a new problem. So weird. Anyway, I don't want to know. I don't want to know what goes on over there. I am terrified to know how the development of this program goes. I'm sure it's a C# fun house over there. Anyway, so getting back to what we were trying to do, I was trying to run the game here. I just wanted to talk about where the lighting was. So based on our current situation, the lighting is actually working quite a bit better than it was working before, but there's a couple things we want to do now. One is we want to try and push the performance a little further than it is right now, because I still think it's too low compared to probably what we need it to be once we start dumping more stuff in there. Now, one thing we could do is we certainly can go ahead and GPUize this potentially if we want to. I don't know how wise that is, but that's something we could certainly look into. But we also have a lot of room left to improve how we're doing things currently on the CPU side for performance. So that's one thing. The next thing that we have to think about, though, as well, is getting further rid of the noise. And I think there's some things that I want to do there. One thing that I was thinking about that I'd like to check out is we've never really verified that we converge to a good solution if we are if we just took a lot of samples, right? So one thing that I think we want to be able to do is like be able to hit a key and run like a single lighting solution that's, you know, really extensive, that takes a long time. And verify that it actually converges to something useful. Or more to the point, maybe make it so that we can just say, look, stop updating the lighting solution from, stop assuming that the lighting solution is changing, just let the lighting solution accumulate over time and just take the total average or something, right? Because right now, I'll be honest, I'm not 100% certain that all the flicker we're seeing is really flicker from sampling. It may be flicker from sampling, but it also may be that we still have bugs in there that we are not accounting for properly. Because I really just can't quite tell at the moment if it's really correct how much flicker there is here, because in some places it looks to me a little like it's maybe more buggy than we might think. And I'm not sure. And as always, it's kind of deceptive because the lighting looks very consistent right now. So when you look at it, it's like, yeah, it looks like it's computing the lighting properly. Certainly that's true, to a certain extent anyway, given the limitations of the system. But on the other hand, it's not immediately clear to me that it's all the way right. Because, you know, it's hard to look at something like this and know if you have maybe more subtle bugs going on in there, right, than what you know about at the moment. So I do think we need a little bit more, I think we need a little bit more information about our scheme, and we need a little bit better ways to test it than what we have right now, because right now we just really don't have any way to know much about subtle bugs that might be lurking in the system. We can see gross error, like we can see things that are really egregiously wrong, but we just don't have a way of looking at things that are maybe more subtly wrong, that we that could be like a source of that noise in addition to honest sampling error. And so rather than try to fight the sampling error right off the bat, I would like a way of sort of getting a little further down that road. So those are two things I'd like to do. Depending on how much time we have, we can look at both this weekend. So if I take a look inside the lighting code, the question is, where do we want to go first? I might go ahead and say, let's look at the lighting code a little bit on the performance side of things today and see if we can't improve that a little bit. So inside compute light propagation, we have been collecting some statistics now. So for example, when we run this, you can see down here we have some statistics that are being tracked. We know how many casts are being initiated, 120,000 rays are being requested, and those are just those are rays that are just initial. The rays in our system don't bounce, right? We send light to surfaces and then we bounce it again on, like we keep bouncing it sort of in a stored state. We don't do paths that go for a long way. So that's total cast 120,000 is the total number we're casting per frame. Okay. So then if you look down there and you look at total leaves tested and total partitions tested, what you can see is that we're testing a lot more partitions than leaves, right? Excuse me. That is probably not great. There's a number of things that we have to consider when we're looking at this. And one of the things that we see, like, we're testing 18 partitions per cast and only 5 leaves, right? And so what that kind of says to me is we're probably wasting too much time testing partitions, because really partitions are supposed to eliminate leaves from testing, right? And so at some point, if your partition number gets too high, then you're really wasting work, because you're just, partition tests tell you nothing, right? Only thing a partition test actually ends up doing is telling you what leaves to test. Now, that's not entirely true here, and I suppose we have to be a little bit more careful about how we talk about this. I probably need one more number here, which is like, and in fact, let's just put it in before we talk about it. Since we allow early outs and we test partitions and use the lighting from partitions, we really need to consider those to be some other thing. They're not leaves, but they're like partition leaves, right? Something like that. And we need to sort of store this information so that we know how many partitions are actually being used as leaves, because that may change our opinion of what's going on and make it look more favorable. We don't know yet. So this will be essentially like, it's not tested, but it's, I guess, used, right? Is maybe the right thing. So total partition leaves used is a thing which basically lets us know how many times that thing has happened. Where is our work? We got to clear those out of our work table somewhere in here, not there. It's in compute light propagation at the top. There it is. So where? Oh, we cleared the whole thing. So I guess no, we don't. So anyway, inside here, we know this is our our raycast here, and when our raycast terminates, right, we know there's two different circumstances. One is that the close enough thing will happen or not, and so that's the thing that we have to check in this case. Because when we come through here, we're going to see if this box has a child count, we're going to count it as a partition. If this box has a leaf, doesn't have a child count, then it's going to be counted as a leaf, right, that we're testing. But then when we get down here, you know, maybe we tested the partition. If we decide in here to push the box on, then it's an honest partition. But if instead we look and see that it's that it was all true here, right, that we exited out after just using it entirely, then it's a partition used as leaves. Right? So that's this value. So if we take a look at that, oh, forgot these have to be padded. It's pretty cool, that assertion. That just saved us a huge speed hit. So here is the new version running the same, but now we get this information here. Oh, but I need to actually output it, which I'm not doing currently. Hold on one second. Let's see here. There we go. So taking a look here at this, we've got a pretty low number actually. So we're not really doing that very much in terms of early outing. We're still going down further to do the more tests. So again, that just strikes me as too many partition tests. So I guess what I would say here is that, you know, if we looked at our split box call, just for starters, when we're doing our split box, I do wonder here if maybe we want to split into, say, 4 boxes, right? Do more of a quad tree kind of a thing. So, or something like that. So, you know, what we could do is say, okay, you know, in general, if you take a look at what happens here, I'm pretty sure there's really no difference. I mean, as far as I can see anyway, there's really no difference between these paths. So what we could do is we could say something like, you know, if zero this out, I think this count B just splits along a plane there, right? And so what we could do is say, all right, if we're going to split along a plane, maybe we can split along 2 planes instead and count them up or something like this, right? So this, for example, is the So this is the one that's KD tree-like, right? It's saying that we're going to take, for any given, let me grab the Milton. What day is today? Day 433. So this is the one that's basically saying, all right, we're going to split things in half, and then we're going to split them in half again, right? So we would do, this is, you know, box A, this is box B, this is box C, splits these in half. What we could do instead is something like, okay, pick two planes, and these are both, split planes are both applied in box A, and then another one's just split in box B, right? So a quad tree or an octree kind of approach, we're basically going to say, let's just go ahead and split these up more aggressively. And I don't know, that's another way we could do this. So if we go ahead and pursue that a little bit further, what we could do is just say, look, anything that's a certain number, this number here is also obviously tunable. I mean, one thing, so before I even do that, right, we can also take a look at what happens if we just say, look, you can have 8 leaves in a child instead. So just to see what happens if we make a shallower hierarchy, for example, would be another thing to take a look at, right? And it looks like that doesn't really change the runtime much appreciably. But you can see that it reduced the number of partitions per cast, right? And it increased the total number of leaves tested. So we could also print out some other values there to help us just understand what's going on more quickly so that we don't have to, you know, do the math in our heads. So we can do something like partitions per leaf. And that would just be total partitions tested over total leaves tested. Syntax error, huh? I agree. So if I run that now, then we can also see like how many partitions we test per leaf. So that's about 1 partition per leaf. Whereas if we change the source count to 4 here, that's 3 partitions per leaf. You know, and you can see those numbers change. It doesn't really change the speed much though. Yeah. I'm also, you know what I'd be interested to know too? If we don't call compute light propagation, what's the speed? I'm not sure why we would get a stack check fail on that. What? So now we see that we actually have bigger problems here. So I guess we kind of saw this the other day. I guess it's worse than I thought. So at the moment, we're actually in a situation where our lighting is not the problem. So we can't really profile below that unless we fix the problem with our shader, right? I mean, you can see that very clearly. So I guess that is that. So we got to go finish up that stuff first, otherwise this is irrelevant. So what happens? What's going on here? So I guess what's interesting about this is because this is overlapped, it gets overcounted. So this is not really telling us. So yeah, so this view actually tells us more what we needed to know, right? Which is that this stuff completed way sooner and there's this huge chunk here that's a problem, right? So we do have to speed up the lighting, but we can't speed up the lighting before we speed up the shading, is I guess what we've learned. So yeah, good to know. So if we take the shading out of the equation, right, then we can actually see more accurately what our time is. Let's see here. No, there we go. So you can see how dramatically this bar kind of grows, right? And then when we get to here, I'm guessing that that is now just like the VSync bar or whatever, right? So I'm interested to know. Let's take a look. We'll take out swap interval. And oops, not what I wanted. We'll take out swap interval and take a look here. So I'm really not sure what this time delay is. We may need to investigate that further, right? I don't know what's taking the time here because it's not pixel shading anything at that point. And that bar doesn't seem to be responsive in the same way that I would expect it to here. So something's weird. So you can see very clearly, right, that we're at 19 milliseconds here or so, or 20. When I come in here, I've spiked all the way up to 29, almost 30 milliseconds per frame, right? And if I look at the threads here, that part's very large, right? Frame display. Debug collation is really not that long, but frame display is huge. And now if I draw us out, it definitely shrinks, but not as much as you would think. Now that may be because of the debug system, right? I'm not 100% certain about that. I think we have a knock at the door. Hold on a second. Look at this graph and figure out what's going on while I'm gone. All right, so they are fixing the heater, or in theory fixing the office heater today. So they will probably, you will see people come in to that, I can't point at it, to that breaker box right there and reset it at some point, assuming it works. All right, so anyway, you know, I think that this is a little bit misleading looking at this thing right here because these lighting threads are accounting for a fixed amount of time that we know about, right? We can see how many cycles that sort of the game update is taking total, and the lighting is accounting for most of it, right? So we kind of know roughly what's going on there. The thing that we don't know is exactly what's going on here. Now, there's a lot of reasons why this might be relatively long. For example, just the fact that we're still doing a lot of texture changes there and so on. We don't really know what's accounting for most of that time. We can profile that using Nsight probably a little bit more specifically, and then we would have a better idea. But again, it's pretty hard at this point to get a sense for how much time the lighting is taking looking at this number. So I think what we're going to have to do is get a little bit more specific about it and be able to print out a number that's more reasonable, that sort of more accurately reflects the total lighting time. And so in order to do that, I think what we want to do is just profile this one directly and then print out the timer directly just for that one. So that we know exactly how long the lighting is taking in a more specific way. I think that's probably all we're going to be able to do for now, until we bounce back over and improve the overall throughput for all this stuff. So I'm going to stop looking at that millisecond number. It's just, we're down to the point where that's just not going to cut it as a way of actually analyzing this information. But what we want to do now is we want to go ahead and take the extra step of putting in some kind of profiling for this that we can measure more directly. So I'm going to take a look at how we might want to do that. It's sort of something we may want in the debug system more properly, I'm guessing. I mean, I'm not 100% sure where that should go, but if you take a look at how we're printing it out here, we probably want that to be something that's going to be usable more than once. Hard to say. Yeah. So I'm not 100% sure how we want to do that. So, normally we've got these timed block things, and so each of those, in the debug system, it's possible that we could do something like, say, this here where we do like the lighting test and we've got, timed function. Maybe we could do something here where we specifically say that we want a function to always show up as its timer. So something where we could say like, okay, we want like a HUD timed function. And the HUD timed function would literally be exactly the same. It would pass something here that lets us know, that it's special, right? And that seems pretty good to me. So if you take a look at what happens here, right, the debug table, that's the stuff here that's globally applicable, we should be able to tell it when it outputs the HUD to grab a specific event value out and to show just that value or just that timer. And that seems like the best thing. That way, in here, we could just do HUD timed function, and then it would show up there, and we wouldn't have to expand the debug window to show it, and we'd get a more stable view of that thing. That's what I think we want to do. So let's go ahead and make that happen as best we can. So let's say we've got a HUD timed function here. That's going to call this timed block stuff, right? And inside the timed block stuff, we probably want to have some way of setting the debug table's information so that it knows that this is important. So the global debug table in here, right, it just kind of knows some stuff. Yeah? So we should be able to do is put what we actually wanted to print out, we should be able to put that in here. And I guess we can just put that by string, probably. So we could put, like, that. Maybe. I don't know. But that seems reasonable to me. So, maybe we go in here and we just say, okay, so a time block is really just where we say global debug table, HUD function equals function. And the debug name I guess we could even use debug name of the function. I don't remember if we need that. I think we do, because this is what it'll be recorded as in the system, I think. So I think we probably just want to set it to the whole thing. So we want to say like, okay, you know, the debug name. The problem is the counter value will, I think, increment twice here. So what we may have to do is do something like this, where we say like, okay, HUD timed function dot is going to call this so that I can put out the name twice. You know what I'm saying? Now, I don't know why we pass the name and the debug name. I guess those are just for friendly printouts. Probably, but I'm not sure. So don't quote me on that. I don't remember when we wrote the system why we had to do that. But yeah, we'll just assume that that's the case. So in here, we've got the HUD timed function, and we're going to go ahead and delete this part from it. And we'll just call this separately with the debug name so that it can get used twice. And it doesn't need anything else other than the var args. And I think you need the paste on there, right? So in theory, that should just work and should create one of these things. And as long as we fix the compiler errors here, which I don't know if there are any, there aren't, that should still just do what it was currently doing. Like, it shouldn't do anything different. The only difference is now it's setting that global variable so that we know which one of those we were inspecting. So compute light propagation, and, well, it wasn't that one. It's lighting test, actually, somewhere in here, right? Lighting test. So lighting test is still getting counted just like it normally would be, and we can go from there. So now if I go down to the debug system proper, in theory where it prints out that HUD, which is probably in the UI, I'm guessing HUD. Let's see, where does that get printed actually? So it's blocks. Oops. So here's where we print this, the HUD line out. Here. So, you know, what I want to do is I want to be able to add something to this that just shows us that HUD function if we're looking at the HUD function. So, you know, if there is one, we'll just like stick it one line lower, you know, or something like that, where we can just print out what the information is. Now, I like how input mouse X and mouse Y are getting passed here for some reason, even though they're not getting used, which is pretty great. In fact, I don't even know what this versus that is. None of these are getting used, right? We've got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So probably used to print them, but we don't print them anymore. So if we take a look at what this is doing, the question here is like, how do we get access to that particular function that we've now got the name of? And so we've got to go double check like how that stuff gets handled. And I think, if I remember correctly, right, we basically have like ways of looking up events in here by their name. I believe that's how we do it, right? Because that's how we were like collating blocks with each other and so on. So here's like some of that stuff. Let's see here. We don't want that. Let's see. Nope. Let's see. Draw element. Top clocks list. Wow, there's a lot of stuff in here. Profile bars. Debug ID. Debug ID interaction. Wow. You know, there's a lot of stuff in here. So I think this is probably what we would need, is to like that debug name is going to be the GUID that we've got there. And so once we have, well, I guess this gives it to us directly. Once we have that, I think we should be able to get the element from it, right? And presumably that would be all we should need, I think. We don't need to parse the name, because that will be done for us. So I think this is all we really need. And that would get us the debug element. Now the question is, does the debug element get us enough? Let's find out. Let's find out. Oops. So this does give us the number of frames. And all of the events that were stored. But it doesn't necessarily give us anything more. Profile node. Yeah, we kind of want this stuff. So you can see here where we do our profile bars, right? In here, this debug profile node is something that we store inside the stored event, right? So we have that information for the stored event, but there's one of those for every frame. So I guess, in theory, if we just query the debug element, that will give us all the frames. We can then do what we wish with that information. We can either knock out the, like, just get one of the frames and print it, or we could look at, like, the running average or the min-max or whatever, right? So I guess that's what I'm going to try. So if we take a look at where that was happening. Did I actually make a change? It says I did. Yes. Okay. So in here, after we do all of the updating in debug end, we're ready to print stuff out. So I should be able to do a format string here, and I should be able to do this, you know, based on whether or not we have something in that slot. So, you know, what I can do is say whatever's in the global table, and I don't know if we've referenced the global table out to a non-global table here. It looks like not. So we'll just take the global table. So if we take the global table and we look at the HUD function, what we can do is do get debug element, that by ID, like get element from GUID, right? And I think we can get it out of here. So debug element, HUD element, or maybe HUD function. We can get the debug element this way. I think we have to pass the debug state for that probably. And then if we have one of those, we can print it out, right? And so let me just do that at the moment. How do we print out strings here? Probably this way. And I think that's probably all I'll do for the moment. I'm going to take a look at the root info size thing. So I feel like for the root info size thing, so we have this tooltip thing. I feel like we basically want that, right? For the most part. So the draw tooltips thing, I feel like we want to just expand that to be a thing that we can use for everything. So something like a debug line buffer or something like this, right? So that when we look at the tooltips here, we just have, instead of it being about tooltips, we just have like a line count and a line text, something like that, so that we just can make these as much as we want. So we have tooltips and HUD. And I feel like that is probably the right thing to do. I don't know, it seems like the most useful. So if we have those two, then instead of the root info, we would just print into one of these. And so if we take a look at where the tooltip stuff is, which the compiler will actually tell me because it's going to not be able to find what it used to be doing. So this stuff right here, we have add tooltips and draw tooltips. We would really have instead something like in here, these would be based on the line buffer. So instead of passing debug state by itself and not saying which line buffer to actually use, we would say debug line buffer, right? And then when you do that, it would know which one you wanted to use. So it goes ahead and does exactly all this stuff here, but now with the new format. So instead of tooltip text, it's line text, right? And then it says, okay, debug state, tooltip count. Again, that's buffer line count. And this is buffer line text, right? Then in here where we actually do this result stuff is ignorable at the moment because it's still going to work exactly the same way. Line text again. And again, all I'm doing is just trying to reuse this code so we don't have two of these sitting around that buffer up some number of lines, because that's just wasteful and, you know, no point to it. So once we've got that, then the same thing would be true for draw tooltips. The only difference is here when we call draw tooltips now, instead, you can see we're doing a particular layout here, and then the layout gets things put into it. What we can do is just pass a different layout. So that way we can pass a different layout and print the root tooltips into the root one and the mouse one into the mouse one, and everything will be fine, right? So here we've got our draw tooltips. We need to be able to pass the line buffer. We probably need the debug state as well, though, because we're going to need like the render group and things like that. Yeah, because we need all like the font metrics and all that stuff, right? So what we're going to do here is anywhere that we were looking for the tooltips before, we're going to instead look for the buffer line count. And then here we're going to use the buffer line text, like so. And these are going to be like draw line buffer and add line. Something like that. Yeah. So let's keep going here. Add tooltip. It's going to be add line. Debug state. Tooltips. Oops. And anywhere we see that, it's just going to be add line. Tooltips. Just say tooltips. So that seems all pretty good. And now we've got, let's see, this stuff doesn't matter. Root info name. So this is actually the root group of the of the debug system that you can like pop down, right? Which I guess we want to keep. Although not really. I'm not sure how we want to do that because the names can't have space in them and we want potentially multiple lines to be printed up there at the top. I mean, I could create another group for it, I suppose, and not do it this way. But I don't love that, right? Meaning this thing is one of those little UI elements that you can kind of put on the screen. And we could just put another one up there. Like if we see a HUD function, then we could have another one up there. I suppose that's not awful. I'm trying to think of how I feel about that. I don't know how I feel about that. I want to keep these changes though. Here we go. And so this should still work exactly the way it was before. I'm just gonna nerf this, meaning our tooltips now just go through that, so we can do more of those if we want to. But I guess so the way we could do this, right, is if you look at what's happening with that root node, that we could just put another node up there that actually is its own UI element. And yeah, I just don't know if I'm not sure how I feel about it. Like maybe that's good, maybe that's not good. It's really hard to say. But if you take a look at what's going on here I don't even remember how this works. Because I thought you could like pull these things off or something. I don't really remember how that stuff worked. It doesn't seem to. Look, we used to have something in there that would clone things. I don't even remember. Anyway, so when we put on this root group thing here, that's just printing a different name into that buffer that was already set up specifically for that. So what we can do here is just, I guess, take the root group that was placed there. Because you can see here, we can just add another tree to the system that just works. So, in theory, if we wanted to, we could just say like, oh, okay, yeah, something like this. Or we just say, all right, there's another one here called functions that we use. And I guess this thing takes the count. 1, 2, 3, 4, 5, 6, 7, 8, 9. Don't ask me why. So we can, if we want to, just say like, okay, we're going to have one of these things. I don't know why there's the root group name and the root info. I guess, like, I don't know why we chose to keep those in two different places. For some reason, it doesn't make a whole lot of sense. But we can make another one of those if we want to. So the root group So I guess that's roughly it, right? And that would create a new one that we could then add to whatever we want, if that makes sense. So we can add another tree here if we wanted to. For example, it could be down at the bottom of the screen instead, or whatever we wanted to do, or on the other end, right? So we could put that one at like right in the middle, let's say. We don't really need the... And I think that would effectively add it to the top as a separate drop-down kind of a box, which I guess is just more the way we were doing things in the debug system. So that's fine with me. So it's been a long time since we did anything here, so I don't really remember how we liked to do things in here or what the design was. But inside here, when we print this out, if we print this out to the function info size, function, debug state, function info, then in theory, should be okay, I would think. Although, make sure that's correct. We set up this group correctly. And we added it. But of course there's nothing in it, which I don't know to what extent that makes a problem. Let me just double check. So when we try to add this tree, it does not like it, however. But I'm not sure why, because it should be okay. Since there's nothing particularly weird going on there. I should compile in debug mode as well, so we can step in and double check. So the problem here is that element is null. So when we go here to draw these, right, you can see we're calling draw trees. When we're in draw trees, we're going through the trees and we get to the one that we just placed, right? So it goes into its group and it's got two children here, it looks like. So you can see that we did print out the name properly, right? So there's the name. And it's listed as having an actual group. I'm going to step in here. So here's our first tree, and this is the regular tree, the one we've had for a while. And so I'm not sure how we got to there from here, because we should have had to loop through this again. So draw tree link is doing that from here? That doesn't make any sense, does it? because you can see, oh, that's the next I was looking at. So this actually is the initial one. Sorry, I was looking at the next one. All right. So then it goes to do the draw tree link. So what's our layout look like here? Let's see here. Group. Oh, we'll do tree first. So this is the actual new one, right? There's the 0. So the other one is at negative, right? It's in the corner. This one's in the middle. So looking at the next and previous, the next one, that's our old one that we used to have. That's normal. So looking at our group does have a child listed in it, which doesn't make any sense because I have no idea. I guess it must be a so it's just a circularly linked list is all. So it doesn't have any children in it, and it just has this one name, and it's got no element. So I'm wondering, but it shouldn't have an element. There's nothing there. So what did we do for this other tree, right? What does it do for an element? Because it's got an element of null as well, but it doesn't seem to have any problem with that, right? So I'm not sure what it's doing that makes that be fine. I guess it's if you don't have children or something, right? So let's take a look at that. So it says it does not have children. So it should skip that. Which it correctly did. And of course the link element is null. So I guess the reason it was working, I guess the problem is that if you have no element and no children, we just never handled that case, I guess. Which doesn't really make much sense because you would think that would have to happen. I guess it never did. It's a bit strange, don't you think? I mean, it seems like that should be there, but maybe I'm wrong about that. So in here, right, this part, I'm not sure what we want to do. I mean, maybe the smarter way to do it is just in debug draw element, right, where we would be using element. Like all this stuff, right, to figure out what element it is. You know, you want it to just do a generic default printout here, right? I mean, that's all we really wanted it to do. So in some sense, right, we kind of have, and I guess one way to look at it would be in here, link.element's only used if we get past the has children thing. So it might be more correct to say like, hey, look, the has children thing is going to be something that we assume if you don't have an element, you must be a child thing. You must be something that can have children, right? Don't know where that function is. Here we go. So I don't really know, like has children and can have children are kind of two different things. So I don't know the degree to which it uses that. It's like has children is really the wrong way to look at it. It's really, it's not has children, it should be can have children, right? And the degree to which you can have children is presumably predicated entirely on whether or not you are an element or just a node in a tree that doesn't have any corresponding element. That would be my assumption. So it seems like this should really be can have children, and can have children is if there's no element. That seems more like it. I don't know. And maybe I'm wrong about that. But looking through here, that seems a little more sane to me. and I'm not sure, right? But so let's go ahead and switch back to release now. So now we correctly have this guy, which in theory, you know, we can do anything we want with. We've got to put some information in here. And does this thing... I don't remember how this stuff was supposed to work. I really thought there was some way to clone these things. Because there's even a clone function in there. I don't know. Anyway, so once we've got this up here, we can now print out the information that we were actually looking for. And maybe we don't want to print the whole thing out like that, because this is just the query name. And so we want to actually just use maybe the proper name for this thing, which is, you know, it's not this unique identifier sort of situation. So in order to do that, inside the debug system where we do that printout, I believe once we've got the debug element itself, then we actually already have that information parsed out for us, I think. Let's see here. So like we've got sort of just this regular name parameter, and I think that might be more what we're looking for, right? So maybe we just want to print out just the name of the function. And that way we can see like, okay, yeah, it's just lighting test, right? Now, if this thing is expanded or not, we should be able to like insert things below it, I would think. So we could try to do that, and we'll see what happens if we do that. But at the moment, what I want to do too is I want to just print out here the millisecond in, total time. And so inside the debug system, when we've got those profile nodes, so it's got duration and duration of children. So I don't know exactly how we're tracking duration and duration of children. But assuming that duration is the total duration, that's the thing that we actually want, right? We want to know like the whole time that it took. So what I'm going to do here is I'm going to say like, let's print that information out. Let's do a 0.02. I don't know if we have a way to relate cycles to milliseconds at the moment. And it's always a little bit dicey to do so anyway, so that might not be right. So what we could do instead is just print out like the cycle count here in some way that's relatively easy to internalize, like kilocycles, let's say, or something like that, or megacycles, should be megahertz. So we could print out like kilohertz or megahertz, something like this. And that seems a little bit more sane. So maybe like kilocycles, I guess we could do, well, it's not cycles per second, so it wouldn't be hertz, right? It's not per second, it's just per frame. So yeah, so we could do something like that. And that seems reasonable, so let's try it. So if I print out this, let's print out kilocycles, or I could just, yeah, we'll do it this way. So if I want to know what this is, and maybe we also want to do like the minimum one as well. So let's say min duration here equals U64 max. And I guess we don't have that. right. So we're going to do the loop over all of the frames for this function that we've got. And we're going to see which one is the most, the lowest. And maybe we'll see which one's the highest as well. And we'll go from there. We could also take an average if we wanted to. So let's go ahead and loop over that. So the debug profile node here, let's get that out. So the HUD function profile node, that's under stored event. Technically, we can put that in here. And so for the stored event, so inside this element, we've got these frames, and the debug element frame has all of the events for this, right? So we have to kind of loop over each frame and then look at the events. So I'm not sure exactly how we have these structured in here, like how we would know necessarily which one of these we're looking at, because I don't remember exactly how we stored functions, right? But if we look through each of the ones that we have here, this is how many events we would have, and we can go through them all and look at what the event is or what the profile node is. And again, I'm not sure how to know which one of the two we have, but presumably it's specified in the debug type, I'm guessing. I mean, that's my assumption anyway. So I'm assuming that in here it's like, okay, depending on which one of these you are, that's going to tell us which of the things you have, like whether you have events or profile nodes or whatever. So I guess we don't really know which of these we've got, and we may need to do some investigation here, right? So let's actually do that. Let's do this. So we know we've got this many frames. And we know on each one we have debug element frame. So for each one of these, we now know that we've got a particular frame of data that we can look at, and it's got this many events in it for that frame. Now, for this, we would expect to only have one event per frame. Well, two events, so the open and a close, I'm assuming. So let's just go ahead and loop over those. Like so. So we can't loop over all these. However, these should have already been collated as well. So again, I'm not 100% sure. We may want to look this up inside the profile tree, right? Because remember, the way that this worked was we have a root profile element. And so maybe we need to look at this a little bit differently. But let's take a look here. So here's where we actually do those profile elements. So you can see here, the element that you're viewing comes through here as root element. And it looks through each of the frames, each of the events, and those events are profile nodes because it's in the profile tree, right? So for us, I mean, it's a little bit tricky because, yeah, I don't know how to get directly to the profile tree from a just the debug events because they're not necessarily going to go into the profile tree, I don't think. Now, maybe that's not true. It may be that functions, that's where they go, right? So let's take a look. So interestingly enough, that does look like how that works. So you can see here, when you do get element from event, it's doing it off of the debug profile group here. So maybe that is how that works. I don't know. We're going to find out in a second. Oh. Let's see here. Just going to stub these out. This way we can have like a min, average, max. Something like that. So if I have I suppose these can just be D. Actually, they don't need to be done that. There we go. So I'm going to step into this line now and see what those actually are. So inside debug end, where we actually, where we actually look at it inside here, I'm going to go ahead and just set a breakpoint so I can find out what we're actually looking at. I don't know why that. Is there a reason this? Does it? Did it not recompile? What's going on there? Did it? Oh, because we're still in slow morning. We're still in O2, so it just optimized out the whole loop, which good for it. It doesn't do anything. That's a good idea. I would have done that too if I was an optimizer. So there's no events for this thing. Okay, then there were just on that one time. That makes sense, I guess, actually. We have to let the frame buffer kind of fill up here. So once we have enough frames to actually fill, then I suppose we're okay, right? Right, as this moves through and fills up frames, then when we stop here, we should start to see some. So there's some events in this particular frame. Here's the most recent one. So if we take a look at what's on here, here's the event. And the profile node version. So let's see, what does HUD functions type evaluate to? It's a begin block type. So a begin block I mean, it looks to me like that actually will store the profile node into here, right? So I feel like if we just look for the end block, that is what we want. So I think this does have the exact information that we're looking for, I think. Don't quote me on that. Debug end. So I think in here, if we just say, although I guess we need to know where the end block is for this begin block, though. So when we come through here, since it's this element is actually in here, this element itself is the begin block, right? So I don't know how that necessarily squares with the way this works here. Yeah, so I don't think it gets one of those, right? I think it should have one of these. So yeah, this is probably inside the profile node. I mean, I think this is what we need. So let's try it, and we'll see. So just inside here, yeah, the... Just looking at the events, I think, would tell us that. Now the question is, per frame, if there's more than one event, what do we want to do about it? I assume we still just want to use the duration either way. But we'll see. So when we come through here and we look at all the events, I think we just want to do debug profile node equals frame node. And once we have this, we can just look at the duration of it, and I think that's all we really need. So we can say, you know, if the minimum duration is greater than the node duration, then the mid duration equals the node duration. If the max duration is less, then it equals. The total duration can just sum. And we want to keep a count, right? And the count doesn't, there can't be that many of them. So now we know how many we did. So as far as figuring out what the current cycles are, that one I'm not sure exactly how to do, because I'm assuming we would have to look at what debug frame we're actually on. And so I guess that's technically, we do keep that in here, I think. That's the viewing frame index, right? So I think that actually is in here. That is in here. So I think if we just said, like, okay, you know, if the frame index listed in the node is the one we're looking at, so essentially we say, all right, if the event frame index, you know, equals whatever the frame order is they're reviewing, then I think that's the cur duration is set there. Don't quote me on that, because I don't know. But let's just say that's true. So then I think all we really have to do is just divide these here. Max, min, and the average we don't actually keep. We only keep the total. So we want to do to divide by 1,000 times the total count. Which is how many of these like we summed up, right? So yeah, I think that's about right. The only thing is, you know, it's not, this is not 100% accurate here because we really should summarize, this should really be summarized outside, I think. Because we're looking per frame, so let's say the thing hits multiple times per frame. I think really what we want to do here is sum the duration this way. So I think we want to do like duration equals 0, then we want to do duration plus equals, you know, event duration, or sorry, node duration. Like that, and then this actually just wants to work off of that value. So that way it's like, okay, if this hit many times in this frame, we're just going to sum them all together and get the total time for this frame, and then we're going to work off of that. Is it frame index? How does this actually work? So in here, inside the profile node, we don't know it. Inside the event, we do know it. And so, yeah, I'm not sure. I'll be honest, I don't really know why we store a frame index here necessarily, because it seems like you wouldn't really need to do that since it's here where that would make the most sense. So I don't quite get that. Like, that doesn't make a lot of sense to me. It seems like the frame index. So who looks at that and why? So you're telling me that that is literally not used? Okay. Well, my intuition was right about it, I guess. I'm not sure how that still stays in there. But I guess it shouldn't be in there. I guess I'm right about that. Well, good. So I assume then, is it safe to say that this frame index here, I mean, that doesn't necessarily line up. I mean, does it or doesn't it line up with whichever frame we're actually viewing, right? So these events in here, you know, they're stored in this array. Does that array necessarily correspond with the ordinals, right? Or are the ordinals unrelated to that? And I'm not sure. So, you know, we could do this and just assume that they are, right? Just say, oh, you know, which one of these are we looking at? But that may not actually be accurate. Not that we super care, because that's not actually a value we particularly care about necessarily. But that is roughly what we want to know, right? All right, so let's take a look here. All right, so we should be able to get some printout now. And I don't know whether we want to go from oldest to newest. So this is a singly linked list, right? And it goes in one particular direction. So if you take a look at, it's got oldest event to most recent event, and then it's got the next pointer. And so the question is, which of these two does it add on to, right? Oops. So looking through here, when this gets added on, so you can see that it's chained off of most recent. So it starts at oldest and goes from oldest to newest. So now we're printing out the min, the max, and the average. As you would expect, the 0 value is in there until we roll the counter, because there's always going to be frames in there that didn't have this getting called until we fill up that entire array. So I think that's mostly all we wanted at this point. So if I go back and switch us to the optimized build, this would give us the actual cycle count that we are taking in order to fill the lighting, right? So here's our sort of min-max average printout. It doesn't look right, though. So you can see here, like, the average value can't be higher than the max, but it is, right? So that's a little busted. So not quite there yet. Getting there, but not quite there yet. All right, so let's go fix that. Oops. All right, so on here, we're going to loop over all the frames. We're going to sum up the duration, which I think is now correctly adding all of the times that we've seen this thing get profiled, right? And then we're going to produce some values here based off of what we've got. So we're going to sum the total count and the total duration, like so. And then we're going to print cur, min. Okay, well, that's probably the most of it. All right. So once this stabilizes, and what we could do is we could drop 0 values. So what we could do is say, look, if in here, if frame oldest event, so don't actually count it if there's no samples on a frame. Just leave those out. So just only sample things, only tell me about frames when we actually called this function. So that'll get rid of the startup, and also if on a particular frame it didn't get called, it just won't profile that one, right? So taking a look here, this looks like what we want, right? So we've got the average, we've got the minimums, that's the fastest we can be, we've got the max, which is the slowest we can be, and we've got our average. So you can see here that to compute the lighting according to this, if it's accurate, it's taking about 61 million cycles, right? And that's, that's still probably way too much. You know what I'm saying? So our job here is to get that number down, right? We want to get that below 61 million, for sure. And what I'd also like to do is, now take a look at these here. So you can see that we've got some of these stats that we were looking at here, where we were trying to say, okay, how many, what's the right balance here for partitions per cast or leaves per cast or whatever. And I sort of played with this value, and we were looking at this here. And so now we can sort of see more specifically if we look at Splitbox. So with the source count here, if we want to change what that number is, right, we can look and say, okay, it's a certain value. We can see how the value changes as we go, what the minimum is, for example, or something like that. Because the minimum is a good indication of like just how fast the thing can be. It's like never going to go any faster than the minimum, right? I'd also like to get out of the business of having this do the crashes on strings. So I'm wondering if we can also make that not happen. We'll see when we get there. So if we take a look at what happens here, you can see if we change it up to 8, it actually isn't flattering for us, right? This actually went up, and our average appears to have gone up as well, right? So it doesn't appear like flipping that up to a higher value really does anything particularly good for us. You know, our min definitely went up. You know, maybe another in-between value is better. I don't know, hard to say. But you can see like it goes down, right? So as we sort of reduce that number, it was definitely going down there, right? So there's a, you know, sort of sitting at 55, average of 63. Let's see if we drop it way down. So then we kind of go back up a little, but actually, no, it's kind of hard to say, right? It's a little bit variable now. It looks like it's almost more variable. And that's where we're testing just a lot of partitions per cast. A lot more, right? But either way, so just looking at it in general, what you can sort of say, though, regardless of anything else, is there's not a lot of play in there, right? It's not like changing that number gets us 2x or something, no matter how we might fine-tune it. We can probably tank the frame rate by making it very high, potentially, maybe, but you know, even that we really can't. So putting a lot of leaves in there really doesn't affect it as much as you might think. So let's keep cranking it up. So yeah, I mean, you know, it's not nothing, but it's not as dramatic as you might like. And so I think one of the things that maybe that tells us a little bit is that, which we kind of already know, is that our spatial partition is not fantastic, right? Which we kind of already knew. But, you know, in theory, modifying the spatial partition that much, we would like it to have a pretty dramatic effect on the total cycle count. And, you know, maybe at the moment, it's maybe not having as much as we would like. But, it did have some. You know, going from 54 to, like, 80 or whatever, that, you know, it's getting closer to doubling, right? That's something. I don't want to be too harsh on it. All right. So looking at those numbers, and again, one of the nice things here is so you can see as we start to do this stuff, right? Those numbers really don't change a lot. And that's what we wanted. So we can sort of take that out of the equation so that instead of looking at very variable millisecond times that can change a lot depending on like what we've got open here and how much we're drawing and all this other stuff, you can see there's like it's a very wide range. There's a whole range of 10 milliseconds it can run through there. These values remain much more stable. And so that's the reason I wanted that, so that we're not sort of chasing a phony thing up here that's going to be variable and weird. This way we can actually see the information more clearly as we're testing. All right, so there's a couple different things about this that's worth looking at. So the first thing that's worth noticing is like, so if we take a look at our raycast function, you know, probably if we're going to stick with box AAB based testing, one of the things that we're not doing right now is we're not really doing that in a very good fashion. So if you look at how we're doing it, we're actually still looping over axes. So first of all, like we could unroll this, certainly, and just have all three cases sort of stacked on top of each other so that there is no loop. Because we don't know to what extent the compiler is able to understand that particularly well. And it may be that we can help it out quite a bit and do less work if we were doing the intersection more cleanly. Also, we don't really know if that's a particularly smart way to do that intersection. So, for example, it's actually very simple to do stuff like closest point on an AAB to a closest point on an AAB to a point is a much simpler function to do than ray intersection. And so I don't know if there's also a similarly easier way to do the ray intersection than what we're doing right now. But my guess is there probably is. So it might make sense to look up some good fast AAB test and just see what people have done that are particularly good. Pluker coordinates. Ah, yes. So yeah, I mean, it seems like going this route could simplify things quite a bit. Let's see what this fellow says here. It's basic ray intersection. So you can actually see going through time here, we are the old school, right? Every face of the AAB test, right? Which is the old way. And you can see them going through different ones here, which we couldn't actually, we haven't done. But this does seem like a pretty nice one. If this actually is a good way to test, we'll have to work through the math here. But looking at this, since all of these are ORs, we should be able to do this SSE-wise pretty well as well, right? You stack them up and then just do one check at the end too, so it should be pretty easy. And since we are testing the ray against multiple boxes, it does line up well with what they were anticipating here, right? Which is that you pre-compute stuff for your ray, which is this information here. So the X, Y, Z, I, J, K, starting direction stuff then gets expanded out into a bunch of things like the inverses of the ray directions and some information regarding the cross terms of those. And so, yeah. So that seems pretty good as well. So we definitely could do something like this, and it looks like we would get a massive speed up from that, because we're just kind of being really dumb right now with how we're doing it. So just cleaning that up could be a pretty reasonable approach. And so what you can see, without actually going through the paper yet, so what you can see here is what they're suggesting at first is just saying like, okay, so let's suppose that we've got all of these planes. Let's just clip the ray to the planes first, and then we'll just see if we have anything left, was essentially what they were saying. So what they said is like, all right, first clip it to this plane, which would give you here, right? Then clip it, to that plane, which would give you here, and that would be further, so you would throw that clip out. Then clip it to this plane, which would give you here, again, further, you'd throw it out. Then clip it to this plane, right? Which is, I guess, well, that would give you like here. So I'm not sure how they deal with that part of it. I'm not sure how they deal with the fact that if you clip it to... Well, I guess what you're trying to say there is that you always take the most interior value of the two clippings. So when you clip to here and here, oh, no, I'm not sure how you deal with that. Because they're not really taking it. Yeah, I don't know. We're going to have to read this because they're not really checking them together with each other. How was this person? This person's was not as simplified. Because you can see, for any individual clipping pair, you're going to get a range that is inside that pair. So I assume you first have to use the pair. You have to respect the pairs in and of themselves, meaning you have to find the min and the max for these two, and then you can clip that min and that max to here and here, and then it would shrink it in, right? I think you've got to do it that way. And it does look like, yeah, so that is what they're doing. So they just say like, look, okay, let's produce a pair, and then we'll clip that pair to the next pair. So we just keep moving it in. That makes sense. And so then you just say, look, whichever the furthest one away was and the closest one, I'm going to narrow in that only that much. I'm not going to ever accidentally flip those two, which would produce the case that I was talking about before where you're like, I don't know what to do with this one, right? So you wouldn't have that problem because you're comparing this one and this one, and then you take this one of those two. Right? So you produce this to here, then you'd get these two, and then finally you'd have the ones in 3 dimensions. So this seems probably, these are pretty darn similar actually. But this looks a little worse because it's got a lot of min-maxing in there. Whereas this looks like they've got it down to actually no min-maxing. Right? It's just 0 tests. So basically you just compute this value, this value, this value, this value, this value, this value, and then you just do tests against 0, or those in with a few greater than or less than tests, and then you're done. Now, one of the problems with this, I suppose, is that it doesn't tell you where. So one problem is, from this, we'd have to figure out whether that gives you enough information to determine the hit. Because that may be a reason like to prefer one that looks like this. because one that looks like this would tell us where. Since we know that the t-min value or the t-max value, depending on which one, if they're greater than 0, right, would tell us. Now, I suppose it's always the t-min value, because if the t-min value was less than 0 and the t-max value was greater than 0, that would mean we started inside the box. And so we would take the other branch. So it's always the t-min in the actual case for processing an intersection. It would always be the t-min. So that should be able to speed us up quite a bit beyond just because this is a crap function at this point. I mean, there's not that much stuff in it, but this loop needs to go. And so if we were to use a more simplified method of checking, then we could get rid of this and we would be out of this business, right? So I think that's probably what we want to do here. I guess we'll do that tomorrow because we're already over time. And we'll see if we can't get those numbers down, and then we can try to improve our spatial hierarchy as well. But at the moment, it seems like that would be a great thing for us, right? Because I can definitely write it this way. I already know how to write it. This way, we're going to have to read more closely because, just looking at this, I have no idea what that tells us, right? I just have to take his word for it. Yeah, I would have to take... Well, it's not his word. I guess I would have to take Eismann, Grosch, Mueller, and Magnor's word for it. Oh my god. I don't know why there are clouds on the screen all of a sudden. So we'd have to take a look at this one and see and understand what this is actually doing. It looks like it would potentially be faster than what the other one is suggesting if you actually get the intersection T from it. If you don't get the intersection T from it, then I don't know that it's actually that useful because we actually need that information. Oops, I did not mean to go to the bibliography. How do I go back? I can't. Okay, that's fine. They don't seem to really talk about this in here. So I guess what I would say is this sounds less good because they are already saying, and assuming they understand their own routine, they're essentially saying that they don't have the computation necessary to determine where the actual intersection occurred. So it may be that we just want to do a t-based test, and this is pretty straightforward. It's just the series of plain tests, right? So we can implement this one really simply, and it would still be an improvement over what we've got now. And it doesn't look like it's quite as good in terms of the minimum number of tests to see whether we intersect. But because we really do need to know the t-value, and you're implicitly computing that directly in this anyway, that just seems like a better plan, right? And it's not like it's that much more work than the other one. It looks pretty comparable, right? This is only doing 2 axes, so you have to add, you know, third in there, and this becomes another, like, this becomes stacked, right? So you're gonna do another round of all of this. But it still seems pretty reasonable, and it does the same sort of stuff as the other one, meaning that it does the inverses pre-computed, which also seems like, you know, pretty reasonable. So yeah. I am kind of tempted to write that now because it gets rid of a lot of this. Let's just see how long it would take. So let's suppose that we wanted to have this part here. So let's suppose in here we just said, okay, we know we want to do the inverses first, right? Because the reason for that is simply that we want to avoid that divide. We want to just be able to do a multiply, if that makes sense. And all, you know, we can check ahead of time to see for the zeros, and if so, we can just make those 0 out, right? I think, if that makes sense. So we should be okay. Let's take a look. And they talk about that a little bit here, right? They basically say, like, okay, where a component of the direction is 0, there'll be infinites, which will make the tmin and the tmax do what we want them to do, right? So in theory, we should be okay with that. And off we go. So all right, so let's suppose we want to do that. First, I need to create one of these guys, one of our v3-4x's, which is going to be our inverse ray direction. And that's just going to be 1.0 divided by the actual ray direction. Did we still call it ray d4x? That was just ray d. Yeah. Right, so we want to produce our inverse, and we can just trust that that'll produce an infinity in the case that we divide by 0 here, because this is going to happen on the SIMD unit, which should have the exceptions turned off for divide by 0. If it doesn't, we'll have to deal with that. We can test that. So once we pre-compute that, this stuff is going to happen essentially the same way that it was before. We have to compute we have to pull the box out of the stack and look at the various children that it has. And then we still need to compute the same stuff. We need to know whether or not we're going to descend into the box and so on. So we're going to start up here, though. And you can see what we want to compute here. Is we want to compute the x and y and z intersections for those slabs in T, right? So let's just work that out ourselves instead of reading the paper, because the paper told us what to do. So I shouldn't say paper, the website publication told us what to do, but let's make sure we can do it for ourselves, right? Because it's very simple and we've already done this before. So if we want to do a pair of these two things here, so let's suppose that we've got our ray. So we've already done ray intersecting plane, and we know that this is a plane, right? And we know furthermore, we know exactly what kind of plane it is. So let's say this is an x-plane. An x-plane is going to have a normal, which is very structured, right? It's going to have -1, 0, 0, as a normal, or 1, 0, 0 as a normal. So this is negative 1, 0, 0, and this is 1, 0, 0. So then when we go to actually determine the intersection in question here, all we're really talking about is where these things are. We know that that's the case, but we also know that there's a specific location where these are as well, right? And we have to deal with that problem too. Okay, so we have our ray origin and we have our ray direction. And we know that what we're talking about here for an equation is we have a ray origin plus t times the ray direction. And what we want to know is when will this end up producing a 0 value for this plane, right? So we want to know if this value right here is our new point that we're talking about. We want to know when we could dot it with this normal, right? And produce 0. That would only be true if it was on the 0 itself. So we really also want a displacement there. So we want to know a particular value here, which is the location of the plane, right? So I don't know what we want to call that value, but that's our constant, right? So we're really talking about this. We're saying that if we add a constant to this thing, then we're going to get 0. We want to know where that's going to be true. And if you look at what this ends up being when you write it out, you're going to get c plus the normal being negative 1, 0, 0, right? This dot product is going to be a pretty straightforward dot product. It's going to get rid of, because remember, a dot product is going to be, nx. We'll call this little thing right here, we'll just call this whole thing capital R. So it's going to be rx plus ny ry plus nz rz, right? We're going to have that dot product in there, but rather than having to deal with that, we just look at the fact that it's an AABB and we say, well, these are gone, right? Because the only thing in here is that x component, and it's either negative or positive 1. So the only things that change are the c and whether this is negative or positive 1. So really what we're looking at is a c plus nx times this here, right? r0x plus t r dx, right? That's all we're talking about, equals 0. And that's the entirety of what we need to compute for that. Now, furthermore, when we solve this, the nx only changes between negative and positive 1 as well. So that's even simpler. So we end up with a c nx r0x plus t nx r dx equals 0. And if we factor for t here, we would just get n. We move this to the other side, negative c, negative nx r0x over this term here, which divides through, right? nx r dx. Right? Now, one of the interesting things here is in this case, we also kind of know I'm tempted, right, to just say, well, I would probably, left to my own devices, maybe even say, let's multiply this by nx over nx, right? We know this is positive or negative 1. So if we did that, we would end up with negative nxc minus r0x over r dx, I think. The reason for that is, so these become squared, and since we know this is either positive 1 or negative 1, if we square it, we just get 1. So I think this is really all we need to do, would be my guess. I think it would just be negative nxc minus r0x over r dx, I think. So this value you can pre-compute for the box. And the other two values are just the ray origin and the ray direction. I mean, that's what it looks like to me anyway. So it looks like you would just have... Yeah, and that looks like exactly what they do. Now, what I'm not sure about there is why the sign is the same for the TX1 and the TX2. I guess because you don't care. So I suppose that's another way of looking at this, right? I guess you could say you don't care which way the normal's facing. So why bother doing that part that I did? Like, why bother saying that? Like, why not just say they both point that direction? Because who cares? Right? And that does seem pretty smart because then, or actually just both point that direction. So it's just both ones. So then really you don't need that value at all. You really don't need that part at all. So that seems even smarter. I did the squared thing, but it looks like the other way is even better, right? So if we did do it that way. So if we did say, okay, what we want to do here is we want to do, the C value plus normal transpose ray origin plus T ray direction equals 0. If we know that this is literally always just 1, 0, 0, no matter which one we're doing, right? Then what we can do is just say, well, okay, if they're always pointing in that direction, then when we hit the plane, all we really need to know is that we've got C plus R0x, because again, we're just picking out the x component now, plus T times RDX, right, equals 0. And then we just need to solve for T. So T equals negative C, negative R0x over RDX. And in this case, if we wanted to simplify from the two minuses, we could multiply it and say C plus R0x over negative RDX, like so, right? So the other thing we could do is just store C negated, and that actually makes a lot of sense too, because if we assume that these were actually the min and the max values, they would appear on this side, right? So we would actually have this, let's say, right? Or constant. And at that point, again, even easier, R0x plus T RDX equals C. And then when you solve, you get T equals C minus R0x over RDX. So yeah, I mean, that's pretty great and pretty straightforward. And then C is just the minimum and the max on the x-axis. I love it. I'm a fan. Yes, good. So I feel like we understand that pretty well. It's really simple. It matches what they've got there, and it makes perfect sense, right? So I feel like that's pretty easy to do. All we have to do is, for our boxes, we need to produce the actual mins and maxes. Now, unfortunately, we're not storing in a min-max form, so we may want to change the storing in min-max form now that we know that that's what we'll be intersecting against. But it's pretty easy to produce min-max temporarily with just one op. So, we can play with whether we want to get rid of this these two extraneous operations here, but in the meantime, it's just plus the radius and minus the radius, right? So we've got the we can get the box min and box max really easily. It's unclear. We may want to get rid of that by storing them in min-max form. That's all. We'll see. That could be costly or it could be trivial. Probably it's trivial, so we probably want to do it. So once we have the box min-max, then we can just do the exact intersection testing on it. So again, we know what it is here. It's just the min. Well, we'll go ahead and do it, and we can do it for all axes at the same time, I believe. I don't think there's any problem with that. So what we would want to do here is an F324x, which is our t value for the box min, and then our t value for the box max. And it's just going to be that. So we've got our box min minus our ray origin. Right, that's our ray origin. And then we want to do the divide by the ray direction. Oops. And that would actually produce, and I guess this is still a V3, right? That actually produces the X, Y, and Z box mins all at once. Because remember, we can just do them that way. There's no real reason not to. It's not any faster. It's still doing all of them. It's just we've got a utility class that does 3 at a time, right? So this would produce all of them. And then our question is just processing those, right? So now what we need to do is we need to take our tmin and tmax and actually produce a single one from that, right? Now this part's a little bit squirrelier, so we now need to think about how we're going to do this. So first of all, we have our xmin and our xmax, which is, you know, the bounds for the x. So we need to like shrink down, shrink down, shrink down, I think is the way we want to do it. I'd have to think it through, but, you know, it would be something like, okay, you know, the F32 4x tmin here, we need to take a minimum of tbox min x well, let's think about this for a second, actually. Let's go back to our little drawing here. There we go. So once I produce my intersection, I have a minimum and a maximum value. But really, I don't know which those are, right? Because I don't know if the ray was pointing backwards or pointing forwards in reference to the mins and maxes. So this is my box min and my box max, but the tmin and tmax might go in either order. So if we were to do it, if we were to do it fully sequentially, and we can probably optimize this, and we'll look, I'm sure they've done that, so we can go look at what they did, but I just want us to go through it once first. To make sure we understand it, right? I never like to implement something I don't understand. Some maybe random number generators. Anyway. So if we take a look at what happens here, right? What we would need to do first is figure out which was the min and which was the max, right? So to start off with, we might say, okay, the tbox min x and the tbox max x, we actually need to take the minimum of those two to figure out which one we actually have. So that would tell us, right, which the minimum is and which the maximum is there. And we probably just need to do that the whole way around, right? So now we would have a tmin and a tmax value that would actually be proper for each of them. It would actually be the bounds for each of them. And then we could successively narrow, right? So then we could say, like, okay, then we've got an F324x, and maybe this is like something like that. And then we could say, for each of the axes we will successively narrow. So we would say, okay, whatever the tmin3 is, I need to take the minimum. Well, okay, so I now know from each of these what our minimum and maximum is in each dimension. We then need to push them the opposite direction, right? So previously what we were doing is saying, let's take the min and max so that we sort which ones we have here, right? So that we know that they go in order. And then what we need to do is we actually need to push them as far in as possible. So if if these are our intersections along the ray, then these are our two maxes, these are our two mins, these are our two maxes, right? We need to take the maximum minimum to get this, and the minimum maximum to get that, right? So here we actually need to take maxes of the mins, as weird as that sounds. And here we would need to take minimums of the maximums. And that way we now would know what our actual bracket was. So now what we would say, I think, is our Tmax value should tell us whether this box is rejectable, right? So I should then be able to say if any are true. So let me go ahead and do the test here. So we essentially have F32 or 0 F32 4x. So if our Tmax is greater than 0, we know that the box isn't entirely behind the ray. Now we may be starting out inside of it, so that we need to know, but it's not entirely behind us, and that's important. So if anything's true in max pass, then we know we actually can process this box. If not, then we don't care about it at all, because it literally can't be hit by us. It's behind us. We can't see it from this ray. Okay. So then this actually needs to be up above, probably, to be honest with you. So this probably needs to get pushed up here to actually, if we're going to try and count that statistic properly. So if we go ahead and take a look at this any true here, then what we can do is we can figure out whether we're in the box by now computing whether the min passes, right? So if the min passes, that's if min is out in front of us as well. If min is also out in front of us, that means we actually hit the box. If min's behind us, but max was in front of us, then we're actually inside the box. And then we would need to descend into it for child testing, right? So yeah. So if any is true in the max pass, or I guess and in the min pass, we don't, because if we know that max passed and a min passed, then we know that the min and the max both passed on that one. It would not be possible for the Tmax to have passed on a different lane than the min pass. Min pass has to pass at least on the same lane as the max pass, if any do, right? So once we know that, is in box is just if any are true. If the child, so let me get rid of these here, right? So once we know min pass, if any true in min pass, then we know we're in the box, right? And so we can actually just do that in here. Otherwise, we got to do the rest of the work. Right? So I'm pretty sure that's right. So we just test to see if any of the max passes are true, then we need to look at this box. If any of the min passes are true as well, then we are inside. I'm sorry. I have that backwards. We need to know. Yeah. So I've got that backwards. Sorry. It's not min pass. It's min fail, basically. And we do need to check to see if they're the same. Yeah. I take it back. So we do need to do... oops. We do need to do this check. And really, I guess we don't even really need to produce quite this. So we just do max pass and. I think that's really all we need to do here. So we basically say, okay, if the max pass is on the same lane as something that was also the t-min was less than 0, then we started out inside the box and we have to consider the box if we can, right? For starting out inside a box that's a leaf box, I don't think we do anything about that specifically. That's kind of just an error to cast from inside the leaf box, but you know, I guess we'll have to deal with that a little bit separately. But anyway, if we take a look in here at the rest of this stuff, so this stuff all goes away now, and hopefully that's why we're hoping for a speed improvement using this technique, obviously. What we want to do here is now skip right down to this part, which we should be able to work out just from the t values that we actually already have, right? So what we should be able to do now is we should be able to say, okay, the t value that we care about updating is out here somewhere, this right here. So this t-ray value, that's what we actually need to update correctly. And so you can see us doing the select on it here. So we have to produce whatever the t hit value is, and it's going to be t-min basically for anyone who actually hits. So what we have to do here is just figure out who actually does hit. And since we've already produced the t-min, all we really have to do is know which ones aren't flipped, right? So really all we have to do here, because here we've checked greater than 0 and less than 0, right? Here we have to check t valid, essentially. And what that would be is if the t-min is less than the t-max. If the t-min isn't less than the t-max, that means that we didn't hit that lane, right? So t-valid is our max for who hit, and t is our actual value that we care about. So we need to know that the t is valid, and then what we need to know is what the actual t-ray is. And to do that, well, I guess that's just the t-min, right? So the mask value that we're going to pick here, again, is just that t-valid. Oh, no, it's not. And they've got to be closer. So the other thing we have to do here to produce our mask value is say we need the t to be valid, and we need the t-min to be less than the one we already had. So if it's not a closer hit, we need to throw it out, right? Close enough is presumably got to be calculated the same way, which is this. And we can change this to t close enough, like so, and just pull that out so that both sides will use the same value. And that can be tested the same way, right? So that'll figure that out, and that will decide whether or not we have to descend or not. Now, we can, in theory, collapse these two a little bit. So since these are pretty simple checks, we could do something like say, look, let's just do these like this. And then we could say, like, look, if it has a child count and either of these two things are true, then we need to make that scalar decision. Otherwise, then we can go ahead and look to see if we need to deal with this branch. Right? So yeah, I think that's roughly what we need. And again, this divide can be changed to a multiply by pre-inverting the ray, which we can, I'll just make a note of. And let's go from there. I don't remember what we specify for this to load. We don't need that yet. So we got to do something about the fact that we don't do a Handmade product like that yet. See what else we got here though. And we don't have min-max, so we've got to add those. Is that it? Oh, right. I meant regular ant. It's confusing because these are scalar, so they have to be ands, the regular kind. Well, they don't have to be, I suppose. This is tmin. So is that. All right. So yeah, so now we kind of have some issues to address here, and this, I guess, will be a little bit more troublesome here. So the problem is we have to be able to return which of these we were actually dealing with, which side of the box we hit. Because, right, we need to know how to use the color information that comes back. And that's actually pretty tough to determine, because that information got lost in here because we don't know which min value we actually used, right? We have them all, but we don't know whether we used the x, the y, or the z, and we don't know which one of those it was. So really, trying to back out that information is pretty tough to tell. So that's going to be a pretty big challenge, actually. Yeah, like... I mean, the only way we can really do it, I think, is seeing where the value we ended up with actually came from. I'm not sure how else to do it, right? Like, in other words, at the end, we've got a tmin value, and the tmin value that we end up with is going to be from one of these mins and maxes, right? It will be tbox min x, y, or z, or tbox max x, y, or z, right? And which one of those 6 it is tells us which face it is, but testing against all of those is kind of expensive. Now, we only have to do it when we actually record a hit. So that's a plus, but it's still nasty. And I'm not sure how to do it in any particularly good way. Because it's kind of just this nasty select operation that just, like, literally has to check. Right? So, I mean, Yeah, I mean, I really don't know what the right way to do that is. But if you imagine what this is going to look like, it's really bad. So it's like... So these are the possible values that we could have ended up with after doing the mins and maxes. And so essentially what you're doing is this. So this will produce a mask value and you just got to bite 6 comparisons, right? I don't know any other way you would do it from that. The price of getting a cheap check is that you don't end up with the information at the end, right? So then you would have to do a thing that says, well, box surface index, right, is going to be an and of the loaded value that corresponds with whichever, one you're looking at. And you just got to do them all. I don't know any other way to do it. So you'd start out and say, well, okay, the box surface index, I guess we'll start out, we don't really need to check this one, because if the minimum x value, I don't know how we ordered our faces exactly, so let's just check. Where's that box side thing? I want the function that actually gets get box surface is the function I actually want. This one. So for each of these, the normal equals... It's basically going to go negative x, positive x, negative y, negative z, positive z. So I'm pretty sure it's just this. Right? So just the minimum x is tmin, maximum x to tmin is if it would be 1. And we just orient the, the ones that pass, right? Whichever one passes is the one that carries the day in any particular lane. And yeah, it's ugly, right? That's 1, 2, 3, 4, 5, 6 versus 2, 2, and the load. So it's, you're talking about something nasty like 1, 2, 3 times 6. Like it's like 18 operations or something just to recover that one piece of information that gets destroyed in the process, right? And off you go. So yeah. On the plus side, I think that is it. So that would be the entirety of the routine. It's still probably a lot better than our old routine, I think. It's hard to say, right? Who knows how good the compiler was at dealing with this? I'm not sure. But I feel like chances are that this is, if once we debug it, will be faster. And we can test them against each other, certainly. So let's take a look and just go ahead and finish off the implementation of the SIMD side of things. So we need mins and maxes here, but that's pretty simple. So let's take a look. if we have an A and a B, and we want to do a min, how do we do that? So it should be pretty straightforward, right? All we should really have to do is do the actual min-max calls, because I believe they both exist in SSE2. So in theory, that's all we have to do for the min and the maxes. And then to do the min and the max for the v3-4x, that should be really straightforward as well, because that's just going to call the other ones, right? So for example, this could be made like this. And I think that's all there is to it. So the only thing that we're left with is the divide. And so for the divide, I guess we probably, since it's vector divide, doesn't really make a whole lot of sense. It's really a Hadamard product here with the inverse, right? Is kind of what we're talking about. We're doing straight across rows. So we can implement the divide operator. I just don't know that we necessarily want to. I mean, it can't really mean anything else, so maybe we just do. You know, who knows? But here's what it would be, right? It'd just be scalar lane divide. Oh, whoops, that's 4x. I didn't want that. I want the 3x. So the v3-4x, if I was to just take operator plus here, operator divide just divides the lanes, then you have that, right? So yeah, so we can run that now, but you know, we would assume we got some bugs in there. I don't know, it's hard to say. Although honestly, that looks pretty similar. So maybe we don't have any bugs in there. But you can see that it definitely got faster, right? It's not like order of magnitude faster, but before we were quite a bit higher. Here we were more like 50, 60. And now we're down below 40, right? And so it's not nothing, right? And we can double check that, because we left both routines in, so we can try compiling different ones in and out interchangeably. Let's look here. So we're at 38 min there. Yeah, and that jumps up to like 60. So the minimum is, yeah, it's at least 20 million cycles saved, which is great, right? Which is very good. So I'd say that's a win across the board. It's still not clear to me that we're doing it right the way that we should be, because again, having to produce this box surface index is kind of expensive there. So that's just kind of a nasty side effect. And I'm not sure there's a lot we can do about that. We could take a look at what happens if we pre-compute the ray. So if we wanted to do a straight across multiplier there, we can. And that just looks like v3-4x invray equals, and we had this up here before. Oops. This just looks like the inversion of the ray direction, like so, right? Of course, I don't know we have to do this. Yeah. So, you know, this is, what's the min running at? It's running at 37,642. You know, it's a little better, right? But it's really not particularly noticeable. You know, that's not really going to make a huge difference, I guess. So the other thing is that we don't really know here, right? We don't really know the breakdown of what's taking what time. You know, if this stuff here was important, we could switch to min and max, and that would be something interesting. We can also get rid of some of our checks here. We don't know how expensive those are. So, you know, for example, we could take a look at what happens if we get rid of some of these checks. So, you know, here's the 36,784 minimum, right? If I get rid of that check, you know, it's actually kind of expensive, right? To store the statistics. So we know the stats are a little bit annoying potentially. Although checking things like that can be kind of, if they're that tiny, can be kind of hard to do because you don't know if maybe just the alignment of the code changed or something, and it's not really the gathering of the stat that was important. It was like the way that it changed where things lined up on the stack or things like this, right? So hard to say. But anyway, you can sort of see where we're going with this. Yeah. And off we go. We can also see what happens nuking this assert. You know, to what degree that affects the runtime. Again, not too much. So there we go. So now that we have that information, yeah, we're also, I don't know what's going on here exactly. Let's run a fresh one. So now that we have that information, and we can also go back and look at the profile now to look at the threads, you can see that that definitely took these down a bit, right? And we're spending a lot more time up in here. So I think, you know, our lighting is actually, at least that pickup computation part, is actually doing a pretty good job of staying within a reasonable frame budget. So that's pretty nice as well. So one of the interesting things too is we can see how elastic this is at this point, because we can always, for one of the things you can do for optimization, right, is we can just crank the stress on the system up way higher, and you know, use that as another way of figuring out how our speed is doing, right? So if I crank that up, we should tank our frame rate massively, right? And so now we should see a lot more, yeah, we would see a lot more variability, I'm sorry, a lot more variation from small changes, because since we're doing a lot more, in theory, right, that would have more of an effect. Hard to say. Anyway, still pretty cool that we've got still interactive rates with that many rays per point being sampled. But you know, another thing, again, like I was saying, I think we need to look a little bit more closely, because I think we still have some bugs with how things are getting recorded. It's only supposed to be able to change up to 1/10, and some of these still flicker even with 256 rays cast and a frame rate this slow. It's just, I think we've got some other bugs in there. So we've got to do a little bit more work on that part. But anyway, I'm happy with that. So let's go ahead and go to a brief Q&A here. I'm happy with that new way of doing the box testing there. surface index lookup table move mask tmin equals box min, and just choose the first bit set in the return from the move max for which index. Well, but you have to do that twice, right? For tmin and tbox max, and then 2 table lookups, and then you have to do a bit scan, right? Although I guess what you're saying is use surface index lookup table to pick the first bit set. Well, no, because move mask does it by byte, right? So you're actually you couldn't really use a table for that, could you? Because the table would have to be too big. Am I wrong about that? We would get an improvement if we switch all the V3 to a V3 for X to load the value into the M128 each frame. Potentially, yes. But I don't know. Usually you want to minimize the memory traffic, so I don't know that that would actually help. Yeah, I don't think a 256 entry lookup table is such a good idea there, though. And are you sure that it would be? I don't actually know that that's true. Alex Kelbo, could you recap how we retain the state of the debug UI between frames? The state of the debug UI, it's actually stored in an actual hierarchy in memory. Yeah, so what I'm trying to say here about the move mask instruction, right, is that we have 4 bytes, 4 bytes, 4 bytes, 4 bytes. So it's going to put 4 ones into the result for every 1 true we actually have. Do you know what I'm saying? So the lookup table for the move mask is going to be huge if you don't first condense it, right? Because it's byte-wise. And there's 16 bytes. So it's going to be 16 bits worth of data, isn't it? Do you see what I'm saying? It ain't going to be 256 bits. Unless you'd have to first opt to condense it. Do you see what I'm saying? You'd have to do like a move mask and then shift the move mask over and or it in. Do you know what I'm talking? You know what I'm saying? Yeah, exactly. So then by the time you do all that, I don't think you've saved any instructions. Right? Because now you need to do 2 of those. So you need to do 2 table lookups with 2 move masks, both that have 3 ops per to collapse them. I think that's slower, dude. If anything, I think that's slower. Because we don't do that much, right? I mean, we'd have to test it to know which one was faster, but here you can see exactly what we're doing here, right? You got to load these values in, right? And, who knows how exactly the compiler is going to decide to do that. But otherwise, you've got an and, an equals, and an or for each step. And you've only got 1, 2, 3, 4, 5 of them. And then 2 more here, right? So you're talking about a very low number of ops. Right? And so if you have to do the move mask in any case, right? You've got to do the move mask. You've got to do the move mask twice, once for the min and once for the max. So you still have to do 2 of these equals and then 2 move masks, right? Then you have to do the collapses on the move masks, which will be at least, what, 2 more instructions per? So that's 4 more instructions there. Then you have to look up into the table. And then you have to actually keep it per lane, right? There's no way. There's no way what you're suggesting is faster. I mean, go implement it and prove me wrong for sure, but that just sounds, it does not sound good. That sounds like definitely slower. Table lookups in general are a good idea. Like what you're suggesting is a good idea. I don't want to dismiss it. It's a good idea, just not for this particular case, I think, because it's so simple. If we were doing something more here, then we, table lookups can be very good. It's just I think this happens to be simple enough that and the table lookup happens to be troublesome enough is the other part of it, right? Sometimes the table lookup's really clean, and in this case it isn't. Rome says, tmin3 will always be the closest in distance to ray origin, since ray d that hits box max will result in t box max less than t box min. No. So if the ray is pointing in the negative direction, then box max will actually hit sooner than box min, right? Because remember, the ray can be going negative direction, down negative x instead of positive x, for example, and then it will hit the x max first, then the x min. Whereas if it's coming from the low and going high, then it will hit min first and max, right? So to be more specific, let's just take a one-dimensional ray, right? So here's my bounds, here's my min, here's my max. If the direction of the ray is going down the positive, right? So it's starting somewhere and going positive, it will hit min and then max, right? First min, then max. But if I started high and I'm pointing negative, then I will hit max first, then min. So we need to do some tests to determine. Now, we could just do that test on the ray direction, right? Because we know it ahead of time, actually. So in theory, we could instead do it this way, where in addition to doing inv ray d here, we just do one test that's the mask for that. So we could say like, okay, ray positive or something, right? And that's just like, okay, if I take the 0 vector and I want to know if the ray direction is greater, right? So I just want to know if the ray is positive down any particular axis, right? And then in theory, down here, instead of actually doing the min or the max, we could select it with a mask that was based on this ray position, right? But it's just not faster, right? This is one operation. So there's just no need, I don't think, for this to occur. We still need the min and the max because we need to know whether the ray intersected at all. So we need to make sure there is room between these two in that way. So, I just don't think you can do anything with that. Does that make sense? So I'm pretty sure that's not something we can actually take advantage of, unfortunately. And so, it is what it is. All right, no more questions. So I think tomorrow what I'd like to do, maybe we'll take a look at the spatial hierarchy just to like finish off some of the optimization stuff. I don't know what to think about the cycle counts currently. 36 million isn't awful, certainly. And it does look like the work is pretty reasonable. So let's pause the profiler. So, you know, I'm just taking a look at this here. So one of the things that you have to think about when you're looking at multi-threaded programming as well is you have to make sure that you're not like wasting too much work. And so what you can see with the multi-threading part of this is we really don't have too much of a problem with drain out. Like, we don't have problems where there's huge gaps up here. So we're pretty well balanced, and you know, I'm pretty happy with that. The amount of time we would save by trying to like use smaller buckets probably isn't much, right? But you can imagine if these buckets were too big, like, so for example, let me just show you what I mean. So in here, right, when we divide up the work, so, you know, let's just say that we divide up the work into much larger buckets than we're talking about here, right? So when we take a look at that, and we look at the threads and we pause that, you can see that the gaps get much larger. And the reason that the gaps get much larger is because the size of the work that we're allocating out is just too big, right? So you end up looking at these threads here, and there's how many? 1, 2, 3, 4, 5, 6, right? They each get one batch of work to do, and then one of them gets the tail end, and the rest of them just have to wait. So you end up with a lot of unused, these threads are just sitting here doing nothing during that time, right? So you typically want to make sure this quanta is low enough, right? And we could imagine, you know, dropping it down and down and down, but I don't think we want to drop it any lower than 256. But you can take a look at how that's breaking down, and you can kind of see how much empty space you're wasting there. And what you want is usually the largest quanta that leaves very little empty space, because that way, you know, you're not spending a lot of time on the bookkeeping and the overhead, but you're still getting, you know, a pretty reasonable amount of that. You're still keeping it very flush. So that's one aspect. The other aspect, and this is the part that we're not looking at currently, is your dead lane count, right? So the other thing that happens is you've got, you know, multi-threading, and so there's one way of looking at dead time is threads are sitting there with nothing to do because there's no quanta to give them. You're out of work, and they're waiting for the last thread that got a quanta of work to do to finish that quanta, right? The other way to look at it is on any particular thread, you've also got lanes. In our case, we've got 4 lanes. That's good. 4 lanes worth of work. And what we're counting on is that these lanes all have active stuff happening in them. But what actually happens is that at some point, lanes get knocked out. They've already computed their results, and the other lanes are still active, so they're just along for the ride. And at some point, you can get into pretty bad scenarios where one ray is still causing the whole thing to go, but the rest of the rays were already done. And so you're essentially losing up to 75% of the computation power computing dead rays. So one of the things that people will do is they'll actually, for lack of a better term, multi-thread the ray. I don't know how to say this exactly. But one of the things that they'll do is, so in here what we do is we just stuff the ray value as one value and do the whole thing, you know, straight through, right? So we get 4 rays in here and we do them all, and that's all we do. If at some point we found that our lane masked out, so we were like, this ray is done, we don't need to compute it anymore, it found its hit or whatever, and we know that, you could replace that ray value with a new ray value, right? And so one way that people will do this is they'll actually, the quanta, it'll pull in new rays as the rays finish and just stay in the ray checking loop, pulling in new rays so that you never lose lane fill. That might be a little bit too advanced for us because then you have to architect your whole thing as like a ray pipeline. So rays are coming in and getting distributed, and you're traversing the hierarchy, and you remember where in the hierarchy you are per ray, and it's a lot more complicated, but it is more not more complicated necessarily to implement, but more complicated to understand everything, and you got to work through a lot more stuff. That may be a bridge too far, but point being, I just wanted to point out that is something that we're not measuring right now. We don't really have a way of knowing how much dead computation time we have, how much computation time we're effectively spending on things that we really just don't care what the result is, because they're just sitting in lanes that are never going to get used anyway, right? So that's something to be aware of. I'll go down the stairs here. So yeah. I don't really have much more to say, so I think we can probably end. I really like the way this lighting is shaping up. I mean, it's so cool that you can get like the lighting in here. It's bouncing off of there and hitting here and stuff, and it gets a little bit of that shine, and it's pretty pleasant. Anyway. All right, folks, I'm going to close it down. Or I'm going to try to anyway. Yeah, so you can see, and we never really finished looking at this because we just implemented it ourselves, but you can see what they did the same thing, right? So they take the min and the max to figure out which one is which, because they don't know, right? They don't even call them min and max to start with. They use the min and max in here for the bounding box, but then just call them 1 and 2. Then they use the min and the max to figure out which one is the min or the max. Then they use the max of the minimums, right? Which is, whoa, this is editable? Okay. And so that's exactly what we did as well, which is what we would think. So yeah. All right. Thank you everyone for joining me for the episode of Handmade Hero. It's been a pleasure coding with you as always. If you would like to follow the series at home, you can always pre-order the game. It comes with a source code. So head to handmadehero.org if you want to play on the source yourself. I will be back tomorrow when we will either continue with the optimization stuff or maybe start to drill down on why we're getting that flicker. I don't think that flicker is entirely due to sampling. I think we've got bugs and we need to fix those bugs. So we'll do a little more debugging on that. Really like how the lighting looks now. I'm pretty happy with it. I think at some point we have to go try playing with the world generation code so that we can actually use the lighting points more effectively than they're being used now. So we've got to kind of work on that back end a little bit. We've got to work on how we're actually going to, use the lighting artistically in the scene. So we're kind of moving slowly towards that part where we'll kind of have a different look at a different side of the lighting, which is, now that we have ways of computing it, and as we get that way of computing it good enough that we think we could use it in the shipping game, we actually need to figure out how we do want to actually use it. And so that's kind of where we're looking at now. All right, until then, hope I see everyone back here for that. Until then, have fun programming. I'll see everyone on the internet. Take it easy, everybody.